For this next section, we're going to look at the Standard Gravitational Model and how it explains main sequence stars and their star life cycles for section 27.2b. So again, our sun being a main sequence star, recently devoted to a yellow dwarf. It's in the class, and that was the swoosh that goes through the middle of the HR diagram. The second and longest stage of life of the star is the main sequence stage. And during the stage, energy, and we're talking about not just electron volts or volts, we're talking about mega in the millions, MeV. It's generated at the core of the star, and it's through a process called hydrogen fusion, in this case, hydrogen atoms. And for my chemistry people, it's the isotopic forms that has deuterium has 1 neutron, and tritium has 2 neutrons, and each one having 1 proton. That's 2 pieces in the middle of the first one, 3 pieces in the middle of the other one. And when these fuse together, they then form helium, which has 2 protons and 2 neutrons. The little graphic here shows deuterium, D, and the T for tritium. The 2 protons are what define an element. So it releases a neutron and 3.5 million electron volts. That's a lot. Because of this release of energy, it usually comes in the form of radiant. And we have also neutrons, as you saw coming off that fusion on the previous slide. And then the plasma particles. That's the parts of the central atom that have charges on them. They're broken up, and we call this solar winds. And you can see the pictures of them, they come off this particular time-lapse photography. We're getting much better. These with the Parker probe that's getting tighter and tighter in orbit around the sun. This will be some of the elements that will form due to this fusion, because we actually get heavier elements as well. For each gram, that's about a weight of 1 paperclip. So if you have 1 paperclip in your hand, that energy release, that mega electron volts talking about, is about 263,000 kilowatt hours of energy. That's what 26 people, typically almost a full classroom, would use in their life in 1 year. So that's just from 1 paperclip. So you can see why science is trying to do a fusion to mimic the star, because of the huge amount of energy released for very little matter. So this is what the hydrogen looks like when it fuses together, H2 for the gas, about a paperclip. So one of those guys breaking apart releases that amount of energy. And this basically again shows you what we have for the deuterium and tritium. And it's in this process, it starts in the center of the core of the atom, but the star itself does not expand, because this outward force from that fusing together these deuterium and tritium, is counterbalanced by the gravity. Again, this is a gravitational model. So the gravity pulling in towards the center of the star. So it reaches a stable, the outward push is roughly equal to the inner pull. And that sets the term of the size of the star. So you have here where the blue shows the gravity being pulled in from all parts of the star, where the red is the expansion through this energy release in the formation of fusion products, helium in particular. So for a main sequence star to remain stable long enough, it has to have an ample supply of hydrogen to fuse together to create helium. In fact, we did not even know helium existed, because we never found it on the Earth until we saw it in the sun's spectrum. Here they showed in the core the helium being created from the fusion of the 2 hydrogen, deuterium and tritium. So that occurs in the core, and this wants to expand in the form of released radiant energy. Outer shell is mostly hydrogen. As long as I have this hydrogen, this fusion will happen in the core. When I start running out of this, then we start generating other situations. The third stage is when almost all the hydrogen is gone within the core. It has fused into helium. In that case, the center of the star, since it's not pushing out anymore because it's not having a chemical reaction or a nuclear reaction, the gravity will start to overcome it. It becomes the big force and starts to push everything towards the center. So if the star releases energy, we have pulsars here, the star itself will start to shrink. And also during this third stage, the inrushing matter, the density, I'm putting more and more material inside of the same volume, the density increases. And when you do, you have more and more collisions with what's left over, the helium, and the temperature from that starts to crush into a point where it starts to fuse and create carbon atoms. And so we have a little graphic here on the right where it shows two heliums will release two neutrons. If you have and then it'll create carbon, which has 6. So you got two deuteriums and tritiums forming helium. The heliums form together to create carbon. And so again, this hydrogen fusion in the helium continues to occur in a shell that surrounds the inner helium core. So if I got helium on the inside because the hydrogen's gone, it's already been fused into helium. As this is crushing in and becoming carbon, it'll create a shell, and the helium is trapped inside, if you will. So we can actually get, as you see here, as a star, we're looking at the center. The helium-helium collision starts to create carbon, but you have a helium shell around that with that helium core. And then the hydrogen, what's left of it still on the outer part. As you see in the green ring, we're losing most of it. So the combined inner core helium fusion into carbon and the outer shell of hydrogen fusion into helium causes the latter outermost shell to expand rapidly because there's nothing now, there's less above it, so it's going to push out. And the gases will cool as the shell expands. They're getting farther apart, they're losing energy. At the expansion stage of the star is no longer a main sequence star. Once this starts to expand out, it's no longer considered a main sequence. But because it's expanding and cooling, that outer surface is getting bigger and bigger and bigger. We start to get what's called a giant. And that's where it's about 10 times the size of our sun. So, and then there's a supergiant that can get 10 times bigger than that, or about 100 times larger than our sun. So these stars get incredibly big. And some of you actually saw that. So here it would show there's our sun at the end of that little arrow compared to one of these supergiants, VY Canis. So it gives you an idea how small a main sequence star is and how big it becomes when that outer shell expands. Lifespan of the main sequence star is estimated to be about 10 billion years, about the amount of hydrogen it has and the rate it reacts. And at the 5 billion mark, it's not a linear, it's a curve. So about 5%, when you get through half of this, about 5 billion years, about 5% of the hydrogen is used up. But this accelerates. And so it's been spent, about the other 95% will be consumed in this second half. So it's not a linear function. It's not at 5 billion, you got half of it. So it's that kind of a graph. About half of its life, about 5% used, the other half, the other 95% is used. So it accelerates quickly. On the fourth stage, the helium fusion creating the carbon atom stops, right? There's not enough helium to create carbon. And when it does, the star loses its outer gases to reveal what's in the middle of its core. So everything else is expanded off, and that core we saw in the beginning, that's all that's left. And this exposed core gets very bright. It'll illuminate the expanding gases, make it appear as if it was a planetary nebula. So it'd be lighting, you see here, it's lighting, the backlighting this gas as it expands. It looks like a planetary nebula, but it's not. Gravity causes the last of this matter surrounding it to collapse inward and leaves a hot, dense core. And we call this a white dwarf. And these guys can shine for billions of years before cooling completely. So it's not a fast process. So if it's even 10 billion, these things can last as that little hot core for billions beyond that. And we'll stop at this point. We've got the 4 stages, but white dwarf becomes a black dwarf when it no longer emits energy. It becomes what's called a dead star or black dwarf.